Perfect.
Well, welcome, Simon.
Yeah, hello everybody. It's really a pleasure to be here. Thanks to Kristen and Sandy for putting this together at this amazing place. Yeah, today I have the joy of being the last to present, but in this case it's actually a joy because I can build upon all the amazing talks we've seen already today, and you will see that some of the same themes will come up again. So I'm interested in tumor heterogeneity, how it emerges and what it means for therapy. So here's first a picture of tumor heterogeneity in a head and neck cancer. And this is spatial proteomics. So you have these kind of markers for cell types, let's say. The details don't matter too much here. And what you can appreciate here is that you have these well-defined regions of normal tissue, like esophagus, germinal center, lymphoid tissue. And then you have the tumor, and if you look at the tumor, you see that, well, the tumor has very different colors. That means the cells in these different tumor regions behave differently, have a different phenotype, and they will also react differently to treatment. So the question is, how does this heterogeneity emerge? And you've heard already a lot about this. I'm not going to go into too much detail, but basically there are two main themes that happen. One is the classical tumor evolution. So you imagine you start with a healthy cell, and then you have mutations. You get new variants. Some of the new variants go extinct. Maybe you have a benign precursor tumor, and then at the end you have this cancerous tumor that makes metastases and it has therapy resistance. So this was the very old classical way of tumor emerges. But that's not all, because now we know, and we've heard today already, that also phenotypic plasticity plays a huge role. So this just means cells adapt their behavior in response to the environment without changing or needing mutations. So this is how it looks like. Imagine you have a cell and it's growing very fast. It might change to a different phenotype where now it's suddenly invading a lot and doesn't divide anymore. And now this doesn't happen in a vacuum, but it depends on the tumor microenvironment. And in this sketch, you see, okay, there's already a lot going on. You have nutrients, oxygen, extracellular matrix, immune cells, stromal cells, and so on. And then, of course, the tumor cells in their phenotype also react with the microenvironment. You get this constant feedback loop that produces this complexity in real tumors. So the big question that's really interesting me is how can we marry these two concepts of the classical evolution and the phenotypic plasticity, and what does it mean for the clinics, right? So for example, here you have recurrence in non-small cell lung cancer after targeted therapy. And the tumor I want to look at today is glioblastoma. So you already are experts on glioblastoma now after Kristen's presentation, so I will run quickly through it. So basically, it's a very deadly brain tumor that after treatment almost always sees a recurrence roughly a year. And it's also characterized by extreme tumor heterogeneity, as Kristen mentioned, both on the genetic and phenotypic level. And you have a characteristic growth pattern where you have this dense tumor core surrounded by this low-density invasive rim. And then there is a, let's say, hypothesis about phenotypic plasticity that can explain this, which is the so-called go or grow dichotomy, that somehow these tumor cells switch between a phenotypic state where they grow very much, or they can switch to a state where they migrate a lot. So the research questions that I had about this was, first, how can we even combine the effect of phenotypic plasticity and tumor evolution? And then if we find a solution, how can we apply it to the go or grow dichotomy in glioblastoma, and what does it mean for the growth of the tumor, and finally for the treatment? So the starting point for this model is that there is a kind of hierarchy of phenotypic plasticity, or you can also say cell decision making. So at the top, somehow you have the genome of the cell, and this only changes if you have mutations or epigenetic changes. And then you have the tumor microenvironment, so together they somehow produce your phenotype that then feeds back to the microenvironment. Now, if you look into detail what is going on, you see something like this. There are thousands of players, and it's almost impossible to make anything out of this, even though people try, of course. So people are looking for simplified models for this. And one of the early papers that I really enjoyed was actually one of Sandy's old papers. I think it's almost 20 years ago, where they said, okay, let's use some neural network for the cell decision making, and maybe the mutations somehow change the weights. So that's really cool. But what I did in this paper was go even more simple. So I just said, okay, let's say we have somehow a function that gives you a probability to assume some phenotype, and it depends on the microenvironment. And in this case, we just distinguish migration and proliferation. And we simplify the tumor microenvironment also a lot, and we just look at tumor cell density as input for this phenotypic switch. So why do we do that? This is just because tumor cell density is actually correlated with almost all the factors that you can think of that feed into these cell decision making, like nutrients, oxygen, extracellular matrix, healthy cells, and so on. So then this is kind of the rough idea, but how do we get to a model? What I chose for this was an agent-based model, in particular cellular automaton, where the cells are either in a proliferating state, which is shown here in blue, or in a migratory state, shown here in red. The migratory cells, they just do a random walk, so they have some diffusive motion. Proliferative cells, they grow with some growth rate alpha. Both of these cells die with some constant rate delta. And then you have these phenotypic transitions between the two states, given by this transition probability R, which I call R, and it depends on the local tumor cell density. Now then, if you think about what kind of this transition probability, if you want to assume something that is not too complicated, some monotonous function, then what you can see is that there are actually two options what the cells can do. So either you have something that is increasing with tumor cell density, where you're more likely to proliferate when you're close to other cells. And this we can think of as a kind of attracting strategy. And it's given by a positive kappa value here. Or you have the opposite, where if the tumor cell density becomes too high, you try to run away. So this kind of a repelling strategy. And then there is one other parameter, which is what I call theta here, which is just a value where you have equal chance of both phenotypes. And if we think about nutrients as causing this phenotypic transition, then you can think of as theta as kind of the global nutrient supply, because then it would mean if you have a lot of nutrients, then the cells would only feel the deficiency of nutrients for very high tumor cell densities, and vice versa. If nutrient supply is very low, then you already feel it at low tumor cell density. So the most important thing to take home is you have this kappa parameter, which is kind of the strategy of the tumor cells, and you have theta, which is the global nutrient supply. So this is phenotypic plasticity, but there's no evolution yet. So this comes now. And the idea is now that each cell has its individual strategy, its individual kappa parameter. And then when a cell divides, there might be a mutation, and then this changes the kappa parameter of the daughter cell. In this case, we just assume some normal distribution here around the value of the mother cell. And that is how you create this heterogeneity in the tumor cell population, and you get this selection of the most fit strategy, let's say. Okay, so with all the ingredients in place, we can look at some simulations, first for tumor growth. And what I show here is now the case where we have small theta, so scarce resources. And interestingly, what you see here is that you exactly see this typical pattern that you are used to from glioblastoma. So on the left here, you do see the cell density with this very high density tumor core surrounded by this low density infiltrative rim. While on the right side, you see this strategy, so the switch parameter, where the cells at the edge of the tumor have this repelling strategy where they try to walk away when it gets uncomfortable, while the cells in the tumor core have this positive value, which means they actually try to grow and they don't migrate. And because the cells can only grow up to a carrying capacity, you can think of as these cells being in kind of a quiescent state. They just know somehow they learned in this evolutionary process, it doesn't make sense for them to try to run away because they will never reach a better place. So they will try to replace their dying neighbor, basically. Okay, and of course, this is just one simulation. Here you can also look at the phenotypes, and you see exactly what I just told you, right? So you have tumor cell density, migrating cells at the edge, proliferating cells in the tumor core, or rather quiescent cells, and then the strategy, which is kind of the genotype. And of course, then I did this for many different combinations of these two parameters, the death rate and the nutrients. And you see you have these kind of three different regimes of tumor growth. And with some mathematical analysis, I could also predict this transition line here, but I'm not going to talk about this now. And you see that, well, there's a special case if there's no death rate, and it's a very boring case. But you have this transition between either you have the case where you have this diffuse infiltrative rim, or you just have the case if you have a lot of nutrients where the cell, where everything does this repelling strategy, you just grow as much as you can and then you try to run away. Okay, so this is nice. So somehow, without even looking at or fitting some parameters, we see that we get this typical glioblastoma growth pattern. But we can also look at treatment. So this was the last part of the questions. So if we start now from these systemic tumors and we do some very simple surgery, remove cells, what's going to happen? Of course, they just going to grow back. But what we can look at now is how long does it take that they grow back? And again, this you see here, this recurrence time, again, for all the combinations of the parameters. And what you can take away from this is that in this model, you see this super high variance of recurrence time, similar to the clinics, actually. And there's no clear, simple, linear, or monotonous behavior. You see that there are these kind of bumps here that are happening. So it's very tricky to predict anything about the patient. But anyway, we don't know the parameter of the patient. So what does it even help us? So in the last steps, what I did was, let's assume we don't know any of the parameters. We throw all the simulations in one black box and assume we have maybe some features that we could measure in the clinic. For example, we could measure some observable of the heterogeneity of the cells. So in this case, what I plotted here is the recurrence time versus the phenotypic heterogeneity. So basically, you just have the growing and migrating cells, and you can take some measure for heterogeneity like entropy. And then you see that there is some correlation. Of course, it's very noisy, but this is not surprising because I also varied the death rate here. Obviously, if you have death rate 0 and death rate is quite high, then there will be a large variability. But still, there's a clear trend that higher phenotypic heterogeneity means worse outcome. Yeah. So to summarize, I asked 3 questions. One was, how can we model this combined effect of phenotypic plasticity and tumor evolution? And I said we need some kind of hierarchy of the phenotypic plasticity with genotype at the top, microenvironment and at the bottom, and these together determine the phenotype, which then feeds back to the microenvironment. Now, if we apply this idea to this go or grow dichotomy in glioblastoma, what we saw is that this actually can predict this kind of typical pattern that you see in glioblastoma tumors. And I derived this kind of map of the evolutionary regimes where I also could predict this transition line with a mathematical analysis. And finally, I saw that if you have high phenotypic heterogeneity in a tumor, then it is very likely that your prognosis is quite bad. So building on this, I'm working on a couple of projects that I quickly want to mention. So maybe some people will now say, well, you didn't include hypoxia, you didn't include a necrotic core and so on. And I know that, and I'm working on that with some people from Spain who have a nice glioblastoma patient data set. But I probably also should talk to Kristin because we could do a lot there. I really enjoyed your talk there. But here the idea is really to add some explicit dependency on oxygen instead of this proxy with the tumor cell density, and have then also the necrotic core, and then can be able to directly match it. Then I'm also interested in looking at different kinds of phenotypic plasticity in the similar vein that Gunnar has just shown, looking at this plasticity between sensitive and resistant states, and maybe look at, okay, can we somehow also do something if you have evolution in there? Not only a fixed transition rate, but the cells could also adapt and have a typical strategy in response to your treatment. And finally, I'm actually also looking at not simplifying this cell decision making too much, but maybe we can actually look at some pathways that we understand. And this I'm doing with the PI of my postdoc, which is Peter Friedl from Nijmegen in the Netherlands, where we're looking at immunotherapy and cancer cell death. So with that, I'm at the end. I'm saying thank you. Thank you to my PhD supervisor, Andreas Deutsch, Babis Hatsekiro from Abu Dhabi, who has worked a lot on Go or Grow models, Peter, which I already mentioned, to students that worked on the paper with me, people that gave us and me money. I'm calling out Moffat again, who were very nice and gave me this travel grant so that I could come here. So thank you for that. And if you want to get in touch, here are some of my socials. So thank you very much. Happy questions.
I had many questions throughout, but I thought others should ask. But I have to ask this one because it's obviously very relevant to a lot of what we do. So a couple of clarifications. How are you modeling nutrients? When your cells mutate, do they mutate only at division? Do they continuously mutate? And how are you choosing that rate? So clarify those two, then I'll have a follow-up question.
Yeah. So nutrients are only implicit in this version of the model. So I just say, you look at some radius around the cell, how high is the cell density? And then I just assume, okay, if it's very high, nutrients are low and vice versa.
Right.
But in the next version, I'm just looking at some multi-scale model with the diffusive factor and then see how this changes things. And about the mutations, I'm only adding a mutation if the cell proliferates. And in this case, I was actually a bit sloppy here because it could also be an epigenetic change. So I basically said, whenever the cell's mutating, you have a small change, like a Gaussian. So a tiny little change to kappa.
Right, so it's plus or minus a little bit on that.
Yes, on the model.
Right, okay, that's kind of intuitively what I thought. So this sort of emergent behavior that you see do you think it's just driven by the fact that those cells are dividing more, therefore mutating more, therefore switching to that more migratory state, whereas the cells in the interior can't divide as much, therefore can't really shift their state?
Yeah, that's a good question. And I'm sure that it's not that because in the simulations, we also have cases where the death rate is very high. So even in the tumor bulk, the cells are dying a lot. So there's a lot of turnover. And so we see adaptation everywhere. So it's not just they grow to a carrying capacity and they don't do anything anymore. So that's not happening. And I also checked and ran simulations where I initialized the system already with a large number of kappa values, like a heterogeneous population, and then only looked at the selection without mutations, and we get the same pattern.
Nice. And final question in relation to that was, when your mass is growing, is that sort of rim, that migratory rim, there right at the beginning, or does it slowly emerge? And then does the thickness of the rim sort of become stationary?
Yeah, it's that. So it slowly emerges. And actually, even though it looks kind of stationary and the width stays the same, I think there is still a change in the kappa values. So from the mathematical analysis, I saw that the optimal kappa, depending on the microenvironment, tends to plus or minus infinity. So even if you have a very old tumor, let's say, there is still evolution going on, and basically these strategies become more and more extreme, so to say.
Okay. Right. Well, I think we're done for today. Thanks for a very nice presentation.